Hey there, classes. Welcome back. We are checking out the movie version of this book right here, The Martian, a fantastic book. And the movie version upon which we're focusing has so many of the themes that we go through in this class that it's one of the only movies, one of two, that we use all the way through. And we go through all of the science, we unpack as it goes. And much of the notes that you see up on the board today are a review. So let's start with what we did in class today. This is a scene from the movie. It's the part of the movie, and if you haven't seen it yet, where Mark Watney, the fictional astronaut once again, is making water. A chemical reaction is making water using rocket fuel, and he's using an iridium catalyst. Catalyst came up in this class because a catalyst helps a chemical reaction happen faster, and in some cases it helps a chemical reaction happen at all. Remember, we have catalysts in our body, enzymes, proteins that help chemical reactions take place. We also talked about the real-world tie-in terms of outside of our bodies with catalytic, there's a word catalyst in there, converters. The things that take some of the harmful gases in gas-powered cars, and as it goes through the exhaust system, it releases the gases by taking out the harmful gases before they make it to our atmosphere. When we were looking at one of our key terms this week, it's a review key term. So I'm going to pull this over for a second. I'll pull this right back. We started with a little bit more, and I know it's over the screen, but I just want to point out density. Density, mass over volume. That was a formula that we had much earlier in the year, and we were reviewing a little bit on density, and I wanted to bring back the whiteboard and talk about all the places that we see density throughout the year. For example, when we're talking about our planet as a whole, the density of our entire planet is around 5.5 grams per cubic centimeter. But when you look at a piece of granite, say at the surface here, it's only about 2.7 grams per cubic centimeter. That tells you that on average, the density of our planet, there must be something very, very dense down the bottom. Now here on my lanyard, I've got a little compass, and the compass, of course, points to magnetic north. When we're talking about the density of the planet later on, especially when we get into plate tectonics, the tie-in here will be the dense material that's down deep in our planet is a rotating molten metal, and that gives us a magnetic field. The magnetic field is incredibly important when we talk about plate tectonics. It's one of the ways that we discovered that there's moving plates on this planet. And when we're talking about plate tectonics, moving plates on the surface of the planet, that has a direct tie-in with evolution. The change in life over time also has a direct tie-in with our planet as a system, our planet as a recycling system of minerals that go down deep into the earth, are extruded or exploded again onto the surface. If it wasn't for plate tectonics, there might still be life on Earth, but it wouldn't probably be nearly as complicated as it is, as complex, I should say, as it is right now. So that's one of the tie-ins right there. Later on, just after this scene in the movie, the fictional character again, Mark Watney, goes to dig up an old radioactive battery. A radioactive battery that they use in space travel, that ties in with our study of atoms early in the year, how some atoms, some elements are radioactive. As they decay, they release energy. In the case of batteries that we use in space travel, even once the battery is beyond its useful life in terms of producing electricity, it is still producing heat. And this, of course, is one of the things that helped Mark Watney deal with the cold as he's driving in his rover to the next landing site where he'll hopefully be rescued. Another tie-in that we want to check out with density is when we get later on in the year to the density of our oceans. For example, pure water has a density of 1 gram per cubic centimeter. See how easy it is in the metric system, 1 gram per milliliter also. The metric system makes it extraordinarily easy to go between units, and also they base the density scale off of water. It's 1 gram per cubic centimeter. That's going to be very, very important, especially when we're talking about climate change, when we're talking about the circulation of the oceans, because salt water has a slightly higher density than fresh water. That will change the ocean circulations. That's one of the things that is changing right now when we're talking about the currents in our ocean changing because the amount of fresh water that is pouring in from melting glaciers. So there's so many tie-ins right here. I absolutely just love, love, love this movie and using it as we go through the year. Also, if you check out one of the other questions over here, let me turn off the screen and pull the next one over. But as we look at the density of Mars as compared with Earth, it gets to one of the main reasons why exploring Mars is wonderful, but having permanent settlements on Mars might not be so easy to achieve. I forgot my clicker, so sorry for walking off the screen there for a minute. When we're looking at the density of Mars, remember Mars is about 1/3 the size of Earth. The density is also lower. Mars, not having as much mass as Earth, has cooled off quite a bit. And compared to our planet, there is no plate tectonic activity on Mars. So when you're looking at Mars as compared with Earth, you're looking at a planet that is just getting blasted by solar radiation. It doesn't have enough gravity because of its less mass to maintain an atmosphere like Earth has maintained an atmosphere. And so if you were to live on Mars, there's billionaires out there saying, we are going to go to Mars, we're going to live there, we're going to establish permanent colonies. No, not in the near future, because when you're looking at the 4.5 billion years that it took to make life possible and make complex life evolve on our planet Earth, the entire theme of our class is the factors that came together to give us oceans, to give us continents, to give us a thick atmosphere, to give us a biosphere that can support humans here on Earth. Well, on Mars, you're essentially talking about what is currently a rock in space, a rusty rock in space. Certainly, it is definitely worth exploring. That's what humans do. We're out in the solar system exploring the planets. That's a good thing. That's what we should be doing. But in terms of saying, well, we're just going to move to Mars and we're going to be a two-planet species, really, when you're talking about the amount of resources it would take to put permanent human settlements on a cold rock that is further out in the solar system, that has 1/3 the gravity, that has no atmosphere to sustain us, no biology to sustain us, you're talking about an extraordinarily huge waste of resources when we're looking at what we've done to our biosphere here on Earth so far. Remember, going back to the beginning of the year, we are currently in the 6th mass extinction. The first 5 mass extinctions, that's when more than half of the species on the planet disappear in a relatively short period of time. 5 mass extinctions have happened over the 4.5 billion year history of our planet. Those 5 were caused by natural events, things like asteroids colliding with Earth, things like intense volcanic activity. When you're looking at the 6th extinction, the extinction event that we're in right now, that is being caused by humans. And when you're talking about the resources it would take to put huge permanent human settlements on a cold rock that's another 40 million miles out, you'd be talking about taking resources that could be much better spent keeping the biosphere that we have, because we are not doing a very good job of it right now. As far as the questions this week, one of the other tie-ins, or all the other tie-ins, are up here. Pull it across. The student's job this week, we have the guest scientists coming to visit on Thursday. They are going to be doing experiments with, guess what, density. The questions that we're checking out this week, just about all of them are a review. These two right here come from what it takes to make a cell, the cell membrane. This will tie in with this one right here when it comes down to when we're looking for evidence of ancient life on Mars, why is it so hard to find that? And again, knocking you over the head with the answer on this one right here, if you're talking about trying to find evidence of ancient life on Mars, you'd probably be talking about some prokaryotic cells. They're not going to leave a whole lot behind in the way of fossil evidence. Remember, most of the fossils that we have today come from things that have shells, come from larger animals. When you're talking about fossilized cell evidence, that's extraordinarily hard, if not impossible, to come by. So it's very, very, very difficult to tell if Mars ever did have life on it in its early history. We know it probably had running water, but if it had life or not, we just don't know. It's very difficult right now to find. However, there is a mission that will go bring some rocks back from Mars all the way to Earth, where we can study them in much greater detail. And using the techniques here with scanning electron microscopes, we might be able to find some evidence for some ancient cells on Mars. Remember, they'd be prokaryotic cells, probably. Very, very simple type of bacteria. What is the density of pure water? It's a review. Remember, it's 1 gram per cubic centimeter or 1 gram per milliliter, same thing. in there. The density of ice. Wait a second, ice floats. That gets back to the tie-in over here. Remember, we compare everything to water. Since ice floats, we know its density has got to be below 1 gram per cubic milliliter. Also, this is a tie-in a little while ago where we were talking about proteins, muscle, fat, things that are inside our bodies. Remember, fat has a density of slightly less than 1. So fat floats. Muscle has a density of slightly greater than 1. Muscle sinks. And when we were talking a little bit about the ratio of fat to muscle in your body, there was the tie-in. That's where we're learning a little bit more about density in this class. Why do we think prokaryotic bacteria evolved on Earth before eukaryotic cells? Remember, eukaryotic cells are the ones where we started checking out all the organelles, all the things that are inside of a cell, the mitochondrion, the Golgi bodies, the nucleus. And prokaryotic cells, you can think of essentially as a little bag of cytoplasm with some DNA basically floating free in there. And when you're looking at prokaryotic cells, they are essentially simpler. That's why we think that they evolved first. And as a matter of fact, the leading idea, the leading hypothesis right now is that at some point in Earth's history, one prokaryotic cell engulfed another prokaryotic cell, and they realized, as much as cells can realize something, they discovered that they had a symbiotic relationship. One perhaps could photosynthesize, get light and energy from the sun directly, and that was the beginning on Earth of specialization within cells. So it's a great tie-in there. And on the chemical reaction part, a little bit of a review. This was the burning of hydrogen in the presence of oxygen. What we saw in the movie with Mark Watney. Mark Watney, just after the scene that I began with, where he's got his hands in the air, he's all happy that he was making some water for his potato crops on Mars. Just after that scene happens, there's an explosion. There was a little bit too much oxygen in his mix. And remember, a chemical reaction, you've got the reactants on one side, you've got the products on the other, and your job is to remember and look back on your notes or look up again if for some reason it escaped your notes. What happens when you have a couple of hydrogen molecules combining with oxygen molecules once you get a activation energy going. Again, hint, hint, look back on our study when we showed the Hindenburg, that big Zeppelin burning in Lakehurst, New Jersey. Good tie-in there with the chemical reactions that we studied so far in this class. Okay, I know I'm trying to cram in a lot into the video, but make sure you get these notes, which will be, of course, at the website, pacificascience.org, and they'll be in your Google Classroom. Make sure you get these on down. These questions along with your notebook being updated will be due by Thursday when the scientists come on in to visit us and walk us through some density experiments. Okay, I know I threw a lot at you there, about 10 minutes there, but have yourself a great week. And as we race on through towards Thanksgiving week, remember we're going to do an extra little bit on all the science. You can do practically a whole trimester on the science of potatoes, on tubers, how they completely changed the culture of Europe, and how they're absolutely essential for this book right here that I keep pointing at. All right, have yourself a great Tuesday, everyone. See you here in class and online.